Alright, so in this video, this is, I believe, the next to last video in our series, we're actually going to talk about some of the factors that affect solubility, and we'll do a little bit of math with it, but not a lot. Okay, so first major thing that can affect solubility is what's called the common ion effect. Common ion effect basically means that if you already have one of the ions in solution somehow, the salt will become less soluble than it already was. Right, so we're going to keep going with our silver chloride here. If I already had some silver in solution, then silver chloride will be less soluble. We'll actually demonstrate that. We have 0.05 molar silver nitrate, so that's our concentration of silver. Now remember, what we know is we know that solubility, so this is from our previous video, of AgCl was normally 1.3 times 10 to the minus 5th molar. Alright, so now we'll figure it out if we have 0.05 molar silver. Now here, I'm going to use one of our ice table shortcuts. Right? Look at the value of KSP. See how ridiculously small this value is, compared to the concentration of silver we already have. So what I'm going to do is that instead of doing out an ice table, where I use 0.05 plus x, that plus x is so small, it's not going to affect the 0.05, not even in the realm of sig figs. So I'm going to ignore the plus x. So here, what I'm going to say is that for our ice table, and I'll just do out the ice table to show you guys, right? So AgCl, Ag plus, Cl minus. Right, so here we already have 0.05 to start with and 0. We're going to gain some amount. We're going to gain some amount. Right, so this is 0.05 plus x. This is x. Now again, what I'm saying is that because this value of x is so small, I'm going to say that it's approximately going to be equal to 0.05. Right, so I'm just going to use that shortcut straight away. So here what we have is we're going to have KSP, Ag plus, Cl minus, right? So 1.8 times 10 to the minus 5th equals 0.05, because that's our silver concentration, times our concentration of chloride, which is just going to be x in this case. Right, so concentration of chloride is going to be 3.6 times 10 to the minus 9th molar. And again, because it's a 1-to-1 dissolution, the concentration of chloride is going to be our value of x. Right, so this is how soluble silver chloride will be if we already have silver. Look at how much less soluble it is because we had silver to begin with. Second thing that can affect solubility is pH. Right, this doesn't apply to everything, but it applies to some things. Because what happens is that if you have a basic substance, basic substances are more soluble in acidic solutions, whereas acidic substances are more soluble in basic solutions. For neutral pH solutions, it's not really going to matter. Right, the reason for this is because of the potential for acid-base reactions. So what we have down here is we have the dissolving of lead fluoride, PbF2. For PbF2, it's not very soluble. But if we add some hydrogen, if we add some acid to it, what winds up happening is that we have an equilibrium where we form hydrofluoric acid, HF. HF, remember, is a very weak acid. Weak acids don't dissociate back. So H plus and F plus, if I actually did this equilibrium arrow justice, would actually look a lot more like this, where it is very, very, very product favored in this reaction. Right? So if we add acid, we pull a lot of fluoride out of the solution. Since we are decreasing the concentrations of one of the products, the reaction is going to shift to produce more product, meaning our salt will become more soluble. Now, if we change PbF2 to PbI2, there's no change by adding acid. The reason why? Hi is a strong acid, so Hi will not combine to take the iodide ion out of solution. It's just going to stay floating there because it normally does that on its own in Hi. Right? So PbI2 pH-wise is going to be fairly neutral, which means no change by adding an acid or a base to it. Now, just to remind you guys a little bit about something you went over sophomore year, which is the types of solutions: saturated, unsaturated, and supersaturated. Remember, a saturated solution has as much substance dissolved as it can hold at that temperature. Basically, what we're saying is that for a saturated solution, Q is equal to K. Right? It's a solution at equilibrium. Unsaturated solutions have Q's less than K, so you can keep adding more solid and it will keep dissolving until you hit the saturated solution. And if you have more substance dissolved, you form a supersaturated solution, so Q is greater than KSP. If you ever have a supersaturated solution, what will happen is that the solution will precipitate until Q is equal to K. Now, usually this precipitation requires some type of disturbance. So, typically the way that you would make a supersaturated solution is you'd make an unsaturated solution at a very high temperature, and then you would cool it down to the point where K changed enough to make Q greater than K. And if you just let it sit there undisturbed and cool gently, you won't see anything precipitate out. You have to disturb it. You either have to agitate it or give some type of way for the crystal to nucleate. Usually, you can scratch a glass or you can add a crystal to the original solute to give places for new crystals to grow. Example of this you guys may have done when you were growing up: rock candy. The initial solution that you let cool down was highly supersaturated, right? And then as you added in the string that was coated in sugar, that created the place for all that excess sugar to crystallize and go back to being an equilibrium saturated solution. So one actual application of this is going to be the ability to selectively precipitate certain ions. Right, so let's say that we had a mixture of two solutions. We have a solution which is a mixture of two different ions. We have copper plus and we have copper 2 plus and lead 2 plus. Right, and I gave you the initial concentrations of each. What I want to do is I want to see what the concentrations have to be of iodide to actually precipitate out just the copper. And I'll show you this right here because I'll actually give you the KSP values. I wanted to actually put these up top. So for copper iodide, KSP is going to be 5.3 times 10 to the minus 12th. For lead iodide, KSP is going to be 1.4 times 10 to the minus 8th. Now, the reason why I can say definitively that copper is less soluble is because both of these follow the same 4x cubed pattern. And since they follow the same pattern, since copper iodide has a smaller KSP value, it's going to be less soluble. All right, so what we'll do is we'll split this up again a little bit. So we'll do our copper iodide and our lead iodide. So copper iodide, what I'm going to figure out from here is I'm going to figure out the iodide concentration needed to start the precipitation. So at what point will this substance not be soluble anymore? So that will be my lower limit to the concentrations. Lead iodide will calculate my upper limit, because once I add iodide past this upper limit, I'm going to start precipitating lead iodide as well as copper iodide. And if I'm trying to separate these two metals, I don't want to do that. KSP is going to be concentration of copper times concentration of iodide squared. So this is going to be our 4x cubed pattern, right? And that's going to be equal to 5.3 times 10 to the minus 12. Right, so copper we were already given here. So I'm going to have 5.3 times 10 to the minus 12 equals 1 times 10 to the minus 4th times concentration of iodide. So I'm going to say iodide squared. And now all I have to do is just go through and solve, right? I don't even need my 4x cubed here, really. I can just do this. So I'm going to get iodide equal to 2.3 times 10 to the minus 4th molar. All right, so if I add at least this concentration of iodide, I'm going to start my precipitation. So that's my lower limit. For lead iodide, I'm going to work with my upper limit. So KSP is equal to PB2 plus I minus squared. Right, so we're going to get 1.4 times 10 to the minus 8th is equal to my concentration of lead is right here. So 2 times 10 to the minus 3rd I minus squared. Solve for I minus. And that's going to give me 2.6 times 10 to the minus 3rd molar. Right, so as long as my concentration is at least 2.3 times 10 to the minus 4th, but not greater than 2.6 times 10 to the minus 3rd, I'm going to precipitate out only copper iodide. So I'll get rid of all of my copper while leaving all of the lead in solution. Right, so this is an example of using the common ion effects to selectively precipitate certain substances out.